Welcome to Yaka Digital Network. When you hear the word chemistry, you might picture a laboratory full of bubbling glass tubes. But chemical reactions are happening all around you, every single second of the day. A chemical reaction is a process of transformation. You start with one set of ingredients, what we call the reactants. They interact, change, and turn into completely new substances, which we call the products. Some of these transformations happen in a flash. When a bota engine burns fuel, the reactants turn into products instantly, releasing a massive burst of energy to push the bike down the road. Other transformations take years. Look at an iron roof slowly degrading after seasons of heavy rain. That is the exact same basic process of reactants turning into products, just moving at a crawl. Knowing why that engine fires immediately while the metal takes years to rest gives us an incredible advantage. Once we understand how these reactions work, we can start to control the physical world around us. To understand how we control them, we have to zoom far past what our eyes can see, down to the microscopic level where elements exist as individual floating particles. Down here, there is a simple rule. For any new product to form, these tiny particles must physically crash into each other. Chemists call this collision theory. But simply bumping into one another isn't enough to make a change. The particles have to hit each other hard. They need enough force to shatter their old structures so they can rebuild into something new. There is a specific minimum amount of force required to guarantee the crash breaks old bonds. We call this activation energy. Every method used to control a reaction comes down to one goal: changing how often and violently these pieces crash together. Millions of different reactions happen every day. The chemists group them into four main categories based on how those starting materials change. The first is combustion. This is what happens when a substance reacts with oxygen to release heat, like burning firewood to cook a meal. The second is neutralization. This occurs when an acid and a base combine. They cancel each other out, leaving behind simple salt and water. You see this in agriculture. If a farmer has highly acidic soil that hurts crop growth, they can treat it with agricultural lime, which acts as a base to neutralize the earth. The third type is displacement. This is a chemical eviction. A stronger, more reactive element steps in and forces a weaker element out of its compound. And the fourth is decomposition. Instead of combining, a single complex substance breaks apart into smaller, simpler pieces. Whether a substance is burning, neutralizing, displacing, or breaking apart, the driving force is always the same: invisible particles crashing together. Since we know everything depends on these collisions, how do we force them to happen faster? We have three main physical tools to speed things up. The first tool is temperature. Heat feeds energy into particles, making them race frantically and collide with much more force. The second is concentration. Packing double the particles into the exact same space makes it incredibly crowded. Moving without crashing becomes impossible. The third tool is surface area. If you have a solid block of a substance, only the particles on the outside can be hit. By breaking that block into pieces, you expose the hidden particles trapped inside. Think of solid maize cobs compared to a pile of fine powder. Grinding the maize exposes every single grain to the outside environment, drastically increasing the area available for a crash to take place. Heating, crowding, and grinding. Each of these methods guarantees that successful, high-energy crashes happen constantly. But there is a fourth, highly efficient way to speed up a reaction. It doesn't require heating or crowding. We can add a special substance called a catalyst. This graph shows the energy needed to start a reaction. Instead of climbing the steep activation energy hill, a catalyst provides a lower tunnel pathway, requiring less energy. It helps the reaction, but remains completely undamaged, ready for the next particle. By acting as a chemical shortcut, a catalyst makes reactions incredibly easy to trigger, saving the enormous cost of generating extreme heat and pressure. Managing these four factors, temperature, concentration, surface area, and catalysts, is the foundation of modern industry. We use them everywhere, from our home kitchens to massive factories. When we want to buy ourselves time, we drop the temperature. A refrigerator simply removes heat to ensure that the chemical process of food rotting slows down to a crawl. And when we need products quickly, we scale things up. Factories use catalysts on a massive scale to rapidly produce vital goods, like agricultural fertilizers, without wasting extra fuel. Controlling these invisible particles translates directly into real-world benefits. It saves us money, preserves our resources, and drives economic growth. From a rusted iron roof to a high-tech manufacturing plant, human progress is tied exactly to how well we manage this continuous, invisible dance of chemistry. Mastering how elements react and combine gives us the practical power to shape, control, and improve our modern physical world. Thank you for learning with us. To watch more videos and access all of our educational content, visit the Yaka website at www.yaka.cc.